Okay, welcome math people. Today we're going to look at the derivative of ln x. So we're going to derive ln x based off the limit definition of the derivative. So let's take a quick look here. So let me just remind you of a couple of things. And so first off, f prime of x by definition is the limit as h goes to 0 of f of x plus h minus f of x all over h. So that's the definition. Now here in this case, we're going to say f of x is ln x. And so in this case, then f prime of x would be the limit as h goes to 0 of ln x plus h minus ln x all over h. So we find this limit, we'll know the derivative of ln x. And so we're going to use some properties of logarithms, etc., and some nice little substitution to evaluate this particular limit. So let me first simplify this using the property of logarithms. So I have logarithms of the same base, that base being e, this being the natural logarithm. And when they're being subtracted, I can condense the logarithms down via division. So therefore, I'm going to write this on another sheet of paper. Therefore, I can write, I can write the limit, I can write ln x plus h minus x as ln x plus h over x. So this is ln x plus h over x, and that's over h there. And so I'll just continue to do some little manipulations to this to allow me to get this limit a little easier. And so what I'll do is I'll divide both these by h, and I'm going to move this divided by h up here as being multiplied by 1 over h. So we'll say the limit as h goes to 0 of 1 over h times ln, so x divided by x is 1 plus, and of course, h divided by x is h over x. All right, so far so good. And so now, kind of let you in on what I'm trying to accomplish here. I'm trying to turn this into e on the inside, the number e. So e by definition, or one of the definitions for e, is that it's the limit as x goes to infinity of 1 plus 1 over x raised to the power of x. So I'm trying to kind of get this particular limit in the form. It may not seem like it's something I can do because this is a limit of something going to infinity, and this is a limit of something going to 0. But there is a way where I can kind of make these correlate. And so that's kind of my aim right now. So that's kind of what I'm working with. So I'm going to do a little substitution. And what I'm going to do is I'm going to introduce a new variable k, and I'm going to let 1 over k equal h over x. And again, I already let you know what I'm trying to accomplish. I'm trying to accomplish something that looks like this. And so if you think about it, if I make this h over x equal 1 over k, then this will be 1 plus 1 over k, which is looking a lot like 1 plus 1 over x. And I'll deal with this exponent in a second now, but still the problem is this is going to 0 and this is going to infinity. Okay, very good. So let's talk about what happens on this particular case. So let me simplify this a little bit. Well, not simplify, let me rearrange this. Let me multiply both sides by x, if you will. And so you will have x over k equals h. And then let me make k go to infinity. So k goes to infinity implies what? So think of x as a constant. And so if this is some constant, theoretically, as k goes to infinity, that implies that h goes to 0. So k goes to infinity implies that h goes to 0. And so therefore, and even from this expression, as k goes to infinity, this whole expression becomes 0. And so that applies if these are equal. Then for this to be 0, that means the numerator is 0. So even from here, you can see as k goes to infinity implies that h goes to 0. So therefore, I can make the following substitution. I can substitute h going to 0 as k going to infinity. I can also substitute the h over x as 1 over k. And then I'm getting closer and closer to what I'm going for. So let me rewrite that again on a blank sheet. And so before I remove this sheet, just showing you what I'm going to do. So I'm going to have the limit, instead of as h goes to 0, I'm going to write k going to infinity because they're equivalent expressions. And also I need to deal with, well, this 1 over h. So let me deal with that real quick. So notice that x over k is h. So if we take the reciprocal of each side, that means that k over x is 1 over h. So I'll turn this 1 over h into k over x. And then ln is ln, 1 is 1, and then a plus the h over x will turn into 1 over k. So let's go ahead and make that transition. In fact, let me write it right here. Actually, I have a little space so you can see it while all this is still going on. So what happens, kind of box this area off, secluded if you will, we'll have the limit as k goes to infinity. Again, as h goes to 0 based off this definition, k goes to infinity. And again, 1 over h is k over x of k over x, ln 1 plus, and h over x is 1 over k, 1 over k. All right, very good. Now, again, what we're trying to do is we're trying to make it look like this. And we got it fairly close. We got the guy going to infinity. We got the 1 plus 1 over the guy. And the only thing we don't have is this exponent. But a property of logarithms is if there's a coefficient here in front of the logarithm, that can be rewritten as the exponent. So this k over x can actually be transported, if you would, there. So I have the limit. So look at everything that I have. I have the guy to infinity, 1 plus 1 over the guy, 1 plus 1 over the guy, and I have the guy as the exponent. Now, I also have this guy. So to make it a little clearer, and now I'm going to use a blank sheet of paper. I think I've kind of utilized as much as I can on this particular paper. So I'm going to rewrite this a little bit and do some operations. So what I had there was the limit as k goes to infinity of ln 1 plus 1 over k to the power of k over x. All right. So when I moved, well, I kind of scratched it out, so it's not over there. But you know, at some point there was a k over x here. When I moved this guy over here, I probably could have left the x because I really only needed the k. So I'm actually going to move the x back if it's okay. So, but I'll make it mathematically clear what I'm doing. So let me rewrite this exponent. This is the limit as k goes to infinity of ln of 1 plus 1 over k. And I write k over x as k times 1 over x. And again, just as previously, I move something from in front of the logarithm to the exponent. I can move something from the exponent to in front of the logarithm. So I'm going to move the 1 over x in front of the logarithm. So it's the limit as k goes to infinity of 1 over x ln 1 plus 1 over k to the power of k. Now, this limit is being evaluated based off k. So the 1 over x has no bearing on the limit. In fact, I can pull 1 over x outside of the limit, but I'll just leave it there for now. But what I want you to see is that this guy, let me get another pen I thought I had another pen. Not sure where. I thought I did have another pen right here. Not exactly sure. Oh, there it is. Well, I got the red guy now, but the red will probably make more of an impact, more of a little pop. So the key is this guy, as we take the limit as k goes to infinity. Well, no, see, I circled too much. I got a little over ambitious. Excuse me. Not the ln part. This guy, pardon the sloppiness. This guy, as I take the limit as k goes to infinity, is going to equal e. By definition, it's e. We pointed out earlier. I'll bring it back just to let you know it's no magic. This is the definition of e. You can write this in a different way, but this is primarily the definition of e. So when I take this limit of this as k goes to infinity, I really just get e. So this becomes, I'll write it to the side here. This is going to equal 1 over x times ln e. And ln e, of course, equals 1. And so this answer is 1 over x. So the derivative of ln x is 1 over x. And if you have a problem understanding why ln e equals 1, remember logarithms were born to find exponents. So just briefly, if I have the log base b of k equals x per se, what this logarithm is trying to find is the exponent that I raised b to in order to get k. That's why logarithms were invented, to find exponents. So this x is actually an exponent. In fact, the same expression in exponential form would be b to the power of x equals k. But more importantly, what this is asking is what power do I raise this base to in order to get this number? So a natural logarithm, ln, is a logarithm of base e. So think about what it's asking. What power do I raise e to in order to get e? And that would be e to the first power to get e. So that's why ln1 is equal to, that's why ln e is equal to 1. And so then in conclusion, we have shown why the derivative of ln x is 1 over x. We'll see you next time.
Specialized in science and mathing, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe-to-toe, impeccable, splitting your back, son, simple as addition and subtraction, black thought, the infinite relax one.